Good evening, and welcome to this evening's program. And as you network and settle down, I'm pleased to invite the Gooseberry Ensemble to enliven the evening with their music. And as you have this moment, may I also request you to please look at your mobile phones and switch them to a silent mode or switch them off. The Gooseberry Ensemble. Ladies and gentlemen, the Gooseberry Ensemble, let's give them a big hand. They'll be back to play for us later. Thank you. May I request you to please take your seats and use this moment to switch off your mobile devices or turn it on a silent mode. And to get the energy up in the room, let's give our Infosys Prize 2024 laureates who are seated here in the first row a round of applause. Thank you. We also have the chairpersons of the juries of the Infosys Prize and the trustees of the Infosys Science Foundation seated here in the first row. And of course, our very special guest for this evening, Professor Peter Sarnak, the Eugene Higgins Professor of Mathematics at Princeton and a member of the permanent faculty of the School of Mathematics at the Institute for Advanced Study. On behalf of all of us here at the Infosys Science Foundation, very warm wishes to every one of you at the start of this new year, and welcome to this evening's program, the 16th Infosys Prize presentation. My name is Deepak Padaki, and it's my privilege to once again be your host tonight. In the words of the late Dr. Abdul Kalam, a dream is not that which you see while sleeping. It is something that does not let you sleep. And so, like the relentless pursuit of our laureates, the Infosys Science Foundation has been on a sleepless mission these last 15 years to recognize and award some of the most brilliant minds in research and scholarship, some of whom have gone on to win even bigger accolades like the Nobel, and to establish a platform where ideas come together and help us understand many of these existential dilemmas that we all face today. I was at the Infosys Prize Winners Symposium last evening, and each of our laureates there presented their work in an intimate gathering about how they're poking and prodding with a purpose, challenging preconceived notions of how things should be, but not necessarily should be. And if I must sum up in one word what I felt connects all their work, it's fascinating. Starting this year, the Infosys Prize takes on a few new dimensions. And to tell you more about this, and for his opening address, I'm very pleased to invite to the podium the president of the Infosys Science Foundation, Mr. Chris Gopalakrishnan.
Good evening, everyone. Welcome to the 16th Infosys Prize ceremony. A special welcome to our chief guest, Professor Peter Sarnak. Since our inception in 2009, the Infosys Prize has honored over 75 exceptional researchers across 6 disciplines: engineering and computer science, humanities, life sciences, mathematical sciences, physical sciences, and social sciences. These laureates have gone on to receive numerous international accolades, including fellowships in prestigious academics and breakthrough discoveries that have advanced their fields significantly. This has been a transformative year for us as a foundation. While continuing our tradition of excellence, we are embarking on a new direction. Our fundamental objective remains unchanged: to inspire and encourage future generation of scientists and scholars in India. However, we are evolving our approach to meet the changing dynamics of research and innovation. From 2024 onwards, we are focusing our awards on early career researchers who are 40 years or younger. This strategic shift This strategic shift reflects our commitment to identifying and nurturing emerging talent at a crucial stage in their careers. For these early career awards, we have established rigorous evaluation metrics that consider research quality and originality, potential for field-defining contributions, leadership in collaborative projects, commitment to mentoring and education, vision for advancing their field. This change aims to provide crucial support when it matters most, enabling promising researchers to pursue bold ideas and establish independent research programs. This year, we have also combined humanities and social sciences as a single category and created a new economics category. This past year has witnessed remarkable scientific achievements that exemplify the power of collaboration. AI has revolutionized our understanding of proteins, the building blocks of life. DeepMind's breakthrough in protein folding prediction has transformed structural biology. The 2024 Nobel Prize in Chemistry recognized the teams behind computational protein design, acknowledging decades of work that culminated in these achievements. In a historical development, the Nobel Committee also recognized the foundational discoveries in machine learning that have enabled today's AI revolution. This acknowledgement underscores how theoretical insights can lead to practical innovations that transform our world. The spirit of open science has grown stronger. AlphaFold's transition to open source has democratized access to cutting-edge protein structure prediction tools. This move exemplifies how sharing knowledge can accelerate scientific progress globally. Let me add something we are doing in India. We have seen extraordinary achievements in India. IIT Madras Dharini project has created a comprehensive brain atlas of second trimester development. This groundbreaking work, accomplished through collaboration among researchers from 5 countries, provide crucial insights into early brain development. The project exemplifies how Indian institutions can lead global research initiatives. To further strengthen international connections, we are proud to announce our new residency program. This initiative will bring our international laureates to Indian institutions for extended periods, creating opportunities for collaborative research projects, mentoring of young researchers, knowledge exchange workshops, and development of joint research programs. The program aims to create lasting partnerships between Indian institutions and global centers of excellence, fostering a vibrant research ecosystem in India. Science today transcends traditional boundaries. The complex challenges we face, from climate change to global health crisis and food security, require interdisciplinary solutions. Our laureates exemplify this approach, working across fields to tackle these pressing issues. As we push the boundaries of knowledge and capability, we must remain mindful of our responsibilities. We are custodians of both our planet's future and the ethical application of our discoveries. Whether developing AI systems or advancing genetic engineering, our work must be guided by strong ethical principles and a commitment to accountability. The Infosys Science Foundation looks towards the future with renewed purpose and optimism. Our commitment to identifying and supporting exceptional talent has never been stronger. Our laureates, both past and present, represent finest traditions of research and scholarship. They are role models for the next generation of researchers who will shape our tomorrow. To 2024 laureates, congratulations. You join a distinguished community of scholars who have set new standards of excellence in their fields. Your work inspires us all and reminds us of the transformative power of research and innovation. Now, before we proceed further with the awards, let us remember Professor Arvind Mittal, our distinguished jury chair for engineering and computer science from 2019 from 2023 to 2023. As Johnson Professor at MIT's Computer Science and Artificial Intelligence Laboratory, Arvind revolutionized parallel computing and declarative programming languages. His contributions to computer architecture and hardware synthesis continues to influence the field today. Beyond academic brilliance, Arvind brought warmth, wisdom, and vision to the Infosys Science Foundation. His mentorship inspired countless young researchers, and his enthusiasm for nurturing talent aligned perfectly with our mission. His legacy lives on in the countless lives he touched and the technologies he helped create. We at the Infosys Science Foundation will deeply miss his presence, his insightful guidance, and his infectious joy for discovery. The video, please. Let us now proceed with the celebration of this year's laureates. Back to you.
Thank you, Mr. Gopal Krishnan. And indeed, Professor Arvind was an integral part of the Infosys Science Foundation and for many years a part of this prize ceremony as well, and will certainly be missed. As we move on now to the award ceremony, may I request Mr. Gopal Krishnan to accompany our chief guest, Professor Peter Sarnak, to their seats on the stage. Thank you. Well, the first laureate that we recognize this evening in this brand new award category of economics is currently a professor at Stanford University in the United States. His socioeconomic research investigates how information diffuses and aggregates through social networks and how it influences their economic choices. To tell you more about our winner's work and to announce the award, it is my absolute pleasure to introduce the jury chair, Professor Kaushik Basu, the Professor of Economics and the Karl Marx Professor of International Studies at Cornell University. Professor Basu is the former Chief Economist of the World Bank and was the Chief Economic Advisor to the Government of India. A Fellow of the Econometric Society, he has published widely in the areas of development economics, industrial organization, game theory, and welfare economics. He was awarded the Padma Bhushan by the Government of India. Please join me in welcoming on stage Professor Kaushik Basu.
Good evening. The Infosys Prize 2024 in Economics is awarded to Arun Chandrasekhar. Professor, Department of Economics, Stanford University, for his contribution to the study of social and economic networks using innovative data and drawing on theoretical models from machine learning, computer science, and of course, economic theory. His collection and mapping of networks data from multiple Karnataka villages provides a testbed for studying important questions for development economics. Arun Chandrasekhar studied mathematics as an undergraduate at Columbia University and did his PhD in economics from MIT. Earlier last year, he was appointed professor at Stanford University. He is one of the world's most accomplished researchers on social networks. Networks are interaction structures among individuals that shape human activity and can substitute for or act as complements for markets. We must recognize that networks can spread information and well-being, but also rumors. Chandrasekhar uses different approaches from theoretical modeling to randomized controlled trials, drawing on techniques from computer science, statistics, and mathematical economics to answer questions pertaining to economic development. He utilizes a variety of methodologies, including observational data, laboratory experiments, and structural and reduced form modeling to investigate these issues and produce policy insights. He has made important contributions to understanding how information diffuses through society and how individuals aggregate information received from others. That helps identify individuals who play a key or pivotal role in the diffusion of ideas and technology through society. Another area of his research is how social learning occurs. Much of our learning is through social interaction, not just through classrooms. And the role played by network geometry in the learning process. His research has important implications for the design of institutions in a world where communication via social networks has become a part of everyday life. Professor Chandrasekhar's work is especially important for developing countries and emerging economies where formal institutions may not work well, and informal networks are critical for facilitating exchange. His research investigates how information diffuses and aggregates through networks, examining the role of individual network positions in shaping some of the big outcomes of our economic and political life. He also studies how networks can promote cooperation among people. Professor Chandrasekhar's research has substantial implications for policy design, informing effective strategies for information dissemination and financial inclusion, and to help us design policies to put an end to poverty. It is high time we did that. He has also made significant methodological contributions to developing innovative and cost-effective methods for network analysis, enabling other researchers to use network theory for social science research. His publications, such as his paper, The Diffusion of Microfinance, published in Science a couple of years ago, have been cited widely and used by researchers around the world. The jury for this year's Economics Prize consisted of Ileana La Ferrara, Seema Jayachandran, Danny Kwa, Trideep Ray, and Sudipta Sarangi, who happens to be here, and me. The jury work for these prizes is always exciting, a process of discovery of cutting-edge research and ideas. As we worked and converged on Arun Chandrasekhar as this year's winner, we had no doubt in our minds that we had hit the right spot. On a personal note, let me add that his research has huge potential, a lot more to come, beyond what has been already achieved. This kind of work can help us navigate the new world of digital networks and enable us to design policies to ensure that the unstoppable march of digital technology turns out to be not a curse, but a blessing. I want to close on a note of caution. The prize is meant to be not just a celebration. It comes with a penalty. It is telling you that as soon as the celebration for the prize is over, you must get up and use your talent to produce even more research of the exceptional quality that is recognized by this prize. Congratulations, Arun.
Thank you, Professor Basu. And before I call him on stage to receive his award, here's a video of Professor Chandrasekhar talking about the web of connections that he's making through his work. Can we have the video, please?
The term social networks has changed significantly over the years since I started my work in social and economic networks. Social and economic networks refers to the web of connections between people, companies, and governments that describes how they interact. And in particular, how different agents here, people, companies, or governments, may face barriers as to who can interact with whom, when, and why. A network visualizes all of these connections, and it shows how relationships expand from one person to many, and this language allows us to highlight that not everybody has the same influence. Some people, even those who might seem not very well connected, might have extremely large outsized impacts. The way we think about what we do as academic economists is that we're storytellers. We're storytellers who are extremely good at math and employ rigor to describe things as sufficiently, precisely, and usefully as possible, but that means at all times we need to remember that we're going to be making errors. We just need to be aware of whether or not the slippages in our stories are going to actually matter when we think about trying to make policy for the poor.
Please join me in welcoming on stage Professor Arun Chandrasekhar. May I request Mr. Mohandas Pai, the anchor trustee for this category, to join us, and Professor Basu for the presentation. May I request Professor Peter Sarnak to present the Infosys Prize in Economics 2024 to Professor Arun Chandrasekhar. Thank you, Professor Sarnak. Thank you, Mr. Pai. Thank you, Professor Basu and Professor Chandrasekhar. A few words. These mics are high.
I'd like to thank the Infosys Science Foundation and the jury for this great honor, and also for spotlighting the role that networks play in economic development. This is a very personal award for me, given both my strong connection to Karnataka and having worked in Karnataka for 17 years at this point. I'm extremely touched. I'm grateful to my mentors, Abhijit Banerjee, Esther Duflo, both who obviously won this award and started JPAL, as well as Matt Jackson and Viktor Chernozukov. All four of them encouraged me to pursue weird ideas without fear. And I'm blessed to be able to write with Emily Briza and Tyler McCormick, my writing partners in some sense, and I thank numerous other co-authors, students, and research assistants. My research is implemented by JPAL South Asia's Bangalore lab in particular, and so I'm privileged to call Gautamma, Shobha, and Sharda, who are here, my colleagues. I've worked with them since I was 22 years old. They taught me how to conduct surveys, how to identify contextually relevant deep issues concerning rural poverty. In survey-based research, you're indebted to those who share themselves with you, They point you towards deeper, pertinent questions, in some sense, the right questions about the world. I'm grateful for the participants in all of my work. And finally, JPAL South Asia falls apart without Tithi, the Deputy Executive Director, my former RA, and sort of the soul of the lab in Bangalore. Finally, a huge thanks to my family, my parents, who encouraged me to pursue wide-ranging interests, my sister for support, and my wife for everything. A fun fact is that my wife is the reason I'm an economist. In my senior year of college, she told me rather than applying to PhDs in math, I probably wanted to do economics instead, and I switched over. So I'm sure the field of mathematics is better to have avoided me, and hopefully economics is better for me joining as well. Thank you.
Congratulations again, Professor Chandrasekhar, for your insightful research. Though, you know, I'm faced with a challenge now when my daughter comes and says she's spending her time on social media as an investment. I need to come up with a more creative answer now. Our next laureate this evening in the field of engineering and computer science is a professor at the University of Washington and leads the Mobile Intelligence Lab there. I was enthralled reading about his work, translating deep research into meaningful solutions that can be easily adopted. The jury chair for this category is the president of Oregon State University, Professor Jayati Murthy. She takes over this responsibility from Professor Arvind Mittal. Professor Murthy is a national leader in higher education training, in teaching, research, and service. Her research interests include nanoscale heat transfer and computational fluid dynamics. She was the first woman dean of the UCLA Henry Samueli School of Engineering and Applied Science, and was also a professor at the University of Texas in Austin, at Purdue, Carnegie Mellon, and Arizona State Universities. The author of over 330 technical publications, she's a member of the National Academy of Engineering, Foreign Fellow of the Indian National Academy of Engineering, a Fellow of the American Society of Mechanical Engineers, and she's won the ASME Heat Transfer Memorial Award, the ASME Electronics and Photonics Packaging Division Clock Award, and the ASME Kate Gleason Award in 2023. Please join me in welcoming Professor Jayati Murthy to the podium.
The Infosys Prize 2024 in Engineering and Computer Science is awarded to Professor Shyam Golakota, Professor, School of Computer Science and Engineering, University of Washington, for his impactful research and technology translation spanning multiple engineering domains in societally relevant areas such as smartphone-based affordable healthcare tools for low and middle-income countries, battery-free computing and communication, and augmentation of human auditory sensing with artificial intelligence. It's my great pleasure to introduce to you Professor Shyam Golakota's research. How shall I describe Shyam's work? Perhaps I should use his own description, that he and his group are not constrained by formal boundaries between disciplines, but will go where the problems take them. One unifying feature of the problems that Shyam tackles is that they are difficult, and every one of them is societally relevant. Shyam has done groundbreaking work in developing intelligent mobile systems for a variety of applications. For example, he has used ambient backscatter to develop battery-free wireless communications. He has used smartphones to create powerful medical technologies for low-resource communities. And he has worked on augmenting human hearing using artificial intelligence, and so much else. Another unifying feature is the sheer creativity of Shyam's approaches, and audacity in the way he picks and solves problems that nobody thought solvable. I believe it is this freedom, this refusal to abide by disciplinary boundaries, that is central to Shyam's success. And the work is not merely academic. His inventions have been used by millions of people all over the world, and to achieve this before turning 40 is truly impressive. So congratulations, Shyam.
Thank you, Professor. And here's a video of Professor Shyam Golakota talking about augmenting humans with AI. Can we roll the video, please?
I've been pretty interested in actually solving real-world problems through technology. The whole idea of augmenting humans and AI is something which I'm super excited about. Think about how AI and humans can complement each other to effectively create superpowers for humans. And in particular, in the case of what we are doing, super hearing capabilities, which is going to transform the lives of people. So AI doesn't really have to be about automating things. You can also use AI to actually enhance the capabilities of all of us. And that could be hearing, vision, intelligence, memory, all these things which can be pretty beneficial. I think the one thing which I have been following is go after problems which other people are not really focused on right now. There's enough smart people out there, they can do it much better. You want to focus your time on solving problems which are important, yet something which are not being given enough attention by a lot of people out there.
Please join me in welcoming on stage Professor Shyam Golakota. May I request Mr. Srinath Bhatni, the anchor trustee for this category, to join us, and Professor Murthy as well. May I request Professor Peter Sarnak to present the Infosys Prize in Engineering and Computer Science 2024 to Professor Shyam Golakota. Thank you, Professor Mufti. Thank you, Mr. Bhatni. Thank you, Professor Sarnak. Professor, a few words from you.
Thank you so much, in particular to the Infosys Science Foundation and the jury for this incredible honor, and to my students whose fearlessness, creativity, and dedication make this work actually possible. I'm here to claim the credit, but they are the ones who are actually doing all the work. My parents are also here. They flew in from Hyderabad, and I feel grateful to share this experience with them. My group's greatest joy and passion is in inventing technology that makes science fiction a reality. As a kid, I think that science fiction movies like Star Trek are amazing, and trying to make them a reality is every kid's dream, and I get to basically live that dream right now. And more importantly, do this in a way in which we can develop technology that positively impacts billions of people across the world. I think this prize is a celebration of that joy, passion, and curiosity, and I'm truly grateful for it. So thank you so much.
Thank you, Professor, for inspiring all the science fiction dreamers that it can become reality one day. And hopefully with these applications, our phone will finally listen to us instead of the other way around. The Infosys Prize consists of a 22-carat gold medal, which you saw being handed to the winners. It weighs 55 grams and a citation and a purse of $100,000 in each category. The winners are selected by juries consisting of eminent researchers from around the world, represented by the jury chairs who are here with us today. Each jury evaluates the achievements of the nominees against the standards of international research, placing the winners on par with the finest researchers in the world. Let us move on now to our next category, Humanities and Social Sciences. And our winner is a professor at the School of History, Classics, and Archaeology at the University of Edinburgh in the UK. He's researching entanglements enabled by oceanic worlds. To tell you more, I'm very pleased to introduce to you the Jury Chair for Humanities, Professor Akhil Bilgrami, the Sidney Morgenbesser Professor of Philosophy, and the Professor for the Committee on Global Thought at Columbia University. He's the author of several books and has been the chair of the Philosophy Department at Columbia from 1994 to 1998, the director of the Heyman Center for Humanities, the director of the South Asian Institute. He was elected Cullman Fellow at the New York Public Library and held the Radhakrishna Chair in India. He's also been the recipient of fellowships and grants from the Mellon Foundation, the Ford Foundation, the National Endowment of the Humanities, as well as the Luce Foundation. Please welcome the very distinguished Professor Akhil Bilgrami.
The Infosys Prize for the Humanities for 2024 goes to Mahmood Kuria for his outstanding and seminal studies of maritime Islam. It has been known for long that when Islam came to India, it acquired in its passage over Persia, Central Asia, and Afghanistan accretions in doctrine and practice, and these sedimented in further deeply transforming local roots in the cultures of India, which it came to inhabit. It can therefore only amount to a kind of fundamentalist revivalism to think that Islam in India is in any sense synonymous with the originary faith of the Arabian lands. But there were as well watery oceanic highways which connected Islam to South Asia and yet further east. And ever since K.N. Chaudhary's influential work, these have been, more recently, the subject of careful and illuminating scholarship. None more careful and illuminating than Mahmood Kuria's, which we celebrate this evening in this award to him of the Infosys Prize. In his major book, Islamic Law and Circulation, which was published by the prestigious series Islamic Studies in Islamic Civilization, Kuria brilliantly elaborates the processes of the globalization across the Indian Ocean rim from the 13th century to our own time, one of the four major schools of jurisprudence in Sunni Islam that owes to one of the earliest Islamic jurists and theologians, al-Shafi'i. With his remarkable linguistic and archival skills, he studies with great scholarly regard the extensive bodies of work over these centuries that molded the development of Shafi'i law in the Indian Ocean, treatises, manuals, commentaries, marginalia that emerged from scholars and educational institutions and led to the formation of what Kuria calls different textual families. And he fastens on one that seems to have been the most prominent, the Minhaj, though it still remains a little obscure to me exactly why this, among the many textual families that existed, acquired the remarkable prominence that it did and prompted Kuria's deep explorations of its global reach. What Professor Kuria presented to us in yesterday's symposium is a bare skeletal sense of one central strand of his work. With his characteristic modesty, he did not mention how demanding his project is. Let me try to explain one kind of steep demand on his kind of scholarship that he so admirably fulfills. The vastly complex and diverse properties of most of the religions we know fall under two broad categories: doctrines, and practices. And some religions, Islam and Judaism in particular, are religions whose doctrines make central the prescriptivity of laws. Law and the texts in which they are consolidated are explicit, codified, discursive, propositional phenomena. And as such, they emerge in the foreground of a doctrine only because of an enabling background of practices, non-discursive phenomena, collective experiences, dispositions, habits, and a range of institutions as well as social memories in which they abide. And so, when the subject is how religious law travels to distant lands via the maritime passages that Kuria so instructively describes, lands where the ongoing practices and non-discursive phenomena are measurably different from the background of practices in which these laws initially arose, there's an enormous amount of negotiation and challenge which they encounter before they settle with some congruence in the zeitgeist of local host cultures. It is these dynamic engagements that Kuria's work presents to us, culminating in distant recanonizations of this particular madhab of Sunni law, amounting, as he puts it in a striking phrase, to the elaborate construction of a Shafi cosmopolis, and demonstrating to us by this insightful construction that he is an intellectual and social historian of the front rank. Our jury, consisting of Professors David Schulman, Kalpana Kanariban, Nirja Jayal, Janet Gyatso, and myself, unanimously chose Mahmood Kuria for the Infosys Humanities Prize, an investment and inspiration, as these prizes are meant to be, for him and for others who will see him and his work as exemplary to rise to new heights of scholarly achievement.
Thank you, Professor Bilgrami. And here's a video of Professor Mahmood Kuria sharing his fascination of what the oceans can tell us in our endless quest for knowledge. Can we have the video, please?
I think I saw the ocean for the first time only when I was a teenager. As a framework, however, I got interested in the oceanic history much later. Before the Portuguese arrival in the Indian Ocean, literature often identified it as an Islamic sea. From the 8th century itself, Muslim communities existed across the Indian Ocean. This long history is significant to understand the history of the Indian Ocean. I started to explore oceanic communities because their contributions to Islamic legal and intellectual traditions were long overlooked. I wanted to go beyond the Arabo-Persian interpretations of Islam and explore the vast oceanic expanse from Cape Town in South Africa to the Sulu Islands in the Philippines. To know how and why they follow a particular strand of Islamic law called Shafi'ism. The most important question that I always ask, what are the indigenous sources? And then it's looking for the voices of the people, the ways in which the communities kept their memories alive. I always enjoy exploring and studying. The desire to understand more and more, yet feeling inadequate, is profound. The more you try to know, the more you feel how less you know. But that is the thing about knowledge.
Please join me in welcoming on stage Professor Mahmood Kuria. May I request Dr. Pratima Murthy, the anchor trustee for this category, to join Professor Bilgrami for the prize presentation. And may I request Professor Peter Sarnak to present the Infosys Prize in Humanities 2024 to Professor Mahmood Kuria. Thank you, Professor Bilgami. Thank you, Dr. Murthy. Thank you, Professor Sarnak. A few words, please, Professor.
First and foremost, thanks to the Infosys Foundation, the trustees, and the jury members for this great honor. More than for me or others who pursued history, I see this as a recognition for all those who supported us when we chose to specialize in humanities and social science in a post-colonial country like India. Especially, I thank my mom, my mother, who worked really hard to send all her children to university, despite only studying up to the 4th standard. Thank you so much, Ma. Also, my siblings, many of whom are here, Jamila, Muhammad Ali, Bashir, Hanif, Shafi, Rafiq, Sadiq, Raihana, and Ashru, as well as my great teachers, Shaykhuna Charushiri Zainuddin Musliya, Dr. Bahauddin Muhammad Nadavi, Professor Yogesh Sharma, the late Vijay Ramasamy, Supriya Verma, and my mentor, one of the mentors, Professor Yang Sung Ho, and Professor Yos Homans, for encouraging me to explore beyond the borders of lands and disciplines, as well as many friends, classmates, colleagues who have supported me at various stages. I dedicated my first book, Islamic Law in the Indian Ocean, to the PhD students out there. Today, I would like to dedicate this award, if I may, to those who completed their PhD but couldn't remain in academia for various reasons. I think particularly of a classmate from JNU. Though we took different paths to engage with the past and the present, Omar, I believe we share similar passion for understanding societies and cultures. In his thought, let us imagine a world that learns from the past, avoids previous mistakes, ensures justice without delay, and allows us to chase our dreams. Thank you.
Congratulations, Professor Kuria. Thank you, Professor Bilgrami. As a French writer, Marcel Proust once said, the real voyage of discovery consists not in seeking new landscapes, but in having new eyes. And as we move from the pathways in the oceans to the pathways in our bodies, I am reminded of Dr. C.V. Raman, for whom understanding the intricacies of our bodies was in itself a journey of endless discovery. In the category of life sciences, our winner is an associate professor in the Department of Biology at IISER in Pune, discovering new connections between bioactive lipids and neurodegenerative diseases. To announce the Infosys Prize in Life Sciences, I'm pleased to introduce the jury chair, Professor Mriganka Sur. Dr. Sur is the Newton Professor of Neuroscience, the Director of the Simmons Center for Social Brain, and an investigator at the Pickover Institute of Learning and Memory at MIT. Prior to founding the Simmons Center, he was head of the MIT Department of Brain and Cognitive Sciences for 15 years. He's an elected fellow of the Royal Society of the UK, the US National Academy of Medicine, the American Academy of Arts and Sciences, and the Indian National Science Academy. Please welcome Professor Mriganka Sur.
The Infosys Prize 2024 in Life Sciences is awarded to Siddhesh Kamat. Associate Professor in the Department of Biology at the Indian Institute of Science, Education and Research in Pune, for his discoveries concerning bioactive lipids and their receptors, and their metabolic and signaling pathways. His research using advanced methods to understand the function of lipids, a key component of cells, has profound implications for understanding the role of these molecules in a range of cellular functions and human diseases. Our winner this year, Siddhesh Kamat, was selected unanimously by the life sciences jury, which included Paola Arlotta, Gagandeep Kang, Satyajit Mayer, Lalita Ramakrishnan, Imran Siddiqui, and myself. Siddhesh is an expert on the biology of lipids, and especially one kind of lipid called bioactive lipids. What are lipids? They are essentially fats, which, along with proteins and carbohydrates, are fundamental constituents of all our cells. In fact, lipids crucially make up the membrane of our cells, or the outer wall. They act as energy sources as well. They make hormones, and through various mechanisms, send signals from outside cells and convey them to inside cells. Lipids, like all fats, do not dissolve in water, as anyone who has put a drop of oil in water knows. Hence, cells need lipid walls to hold together a very large number of molecules inside them and not have them dissolve away. But lipids form more than just containers for cells. I'll give you two quick examples of their importance. First, you've all heard about cholesterol. It's a lipid that is made by the body to make parts of cell membranes as well as hormones and vitamins. Cholesterol combines with proteins to make lipoproteins for transport through the blood. High-density lipoprotein, or good cholesterol, is used for transporting molecules and fighting inflammation. Low-density lipoprotein, or bad cholesterol, accumulates in blood vessels and can cause heart disease and stroke. So understanding lipid function and metabolism is crucial for understanding the biology of cholesterol. A second example is on the role and importance of lipids comes from brain diseases, especially Alzheimer's disease. The Centers for Disease Control in the USA estimates that 1 in 9 people, or 11% of people over the age of 65, are stricken with Alzheimer's. And 33%, 1/3 of people 85 and over, will have cognitive decline related to Alzheimer's. Lipids are now seen as a central player in Alzheimer's disease because increased levels of lipids cause excess production of amyloid beta, which is a complex protein that forms plaques in the brain and kills neurons or brain cells. The major risk factor for Alzheimer's disease is ApoE4, a gene that makes apolipoprotein 4, which is involved fundamentally in lipid transport and metabolism. And phospholipids, a form of lipids which are the major constituent of brain cell membranes and lipid rafts that make synapses, degrade with age, and contribute directly to the onset and severity of Alzheimer's. So we have lipids, we have phospholipids, which are all very abundant in the body, and then there are bioactive lipids called lysophospholipid, and our winner today is an expert on a subset known as lysophosphatidylserine. It's a mouthful, so I'll call it lyso-PS. These are less abundant, but nonetheless crucial for cell function. These are very complex biological molecules. They are not easy to study. To understand them, you need to understand how they are made and use very sophisticated methods of chemical biology to understand their functional properties and mechanisms. Siddhesh has emerged as a world leader in the study of lyso-PS. He has discovered their role in signaling within cells, including immune responses to oxidative stress and their potential involvement in forms of cancer. By modifying these lipids, his group has discovered how they work. He's shown that in the brain, they act through a specialized receptor, and they enhance brain inflammation associated with certain neurodegenerative diseases. The fundamental biology he's studying is essential for developing diagnostics and therapeutics for a range of disorders and diseases. And finally, the jury strongly appreciated the technological innovations and collaborative spirit of Siddhesh's work. He has set up a leading-edge lipidomics facility at ICER Pune, and he has generously collaborated with many researchers in diverse areas of biology to enable progress. So congratulations, Siddhesh, on receiving the 2024 Infosys Prize.
Thank you, Dr. Sur. And before I call him on stage, here's a video of Dr. Siddesh Kamath talking about what got him started on lipids.
Throughout my formal education, I have never taken a course in biology. So I found a way to study biology through chemistry. Everybody knows lipids that are found in food, like cholesterols. But there are a class of lipids called bioactive lipids, and they basically regulate different biological processes. So we figure out how this is regulated and what happens when the concentration levels of these bioactive lipids are disrupted. Specifically, one class of such bioactive lipids which are called lysophosphatidyl And what we want to do now is to figure out where in the metabolism of lysophosphatidyl can we intervene and develop a therapy. A lot of the disease models that we are working on currently in the lab have no cures. When we started the lab, I realized that there were virtually no labs in India doing lipidomics. We have generated a lot of knowledge, and my desire is to have at least one thing that has come out of my lab to be in practical use, whether it is technology or a drug.
Please join me in welcoming on stage Dr. Siddesh Kamath. May I request Mr. S.D. Shibulal, the anchor trustee for this category, to join the stage, and Dr. Sur as well. May I request Professor Peter Sarnak to present the Infosys Prize in Life Sciences 2024 to Dr. Siddesh Kamath. Thank you, Mr. Shibulal. Thank you, Dr. Sur. Thank you, Professor Sarnak. And Professor Kamath, a few words from you, please.
First, I wanted to express my gratitude to the Infosys Science Foundation for organizing 2 wonderful days of scientific and social events. It has been a tremendous experience and honor to participate in these events along with the other laureates and distinguished guests. I also thank the Life Science jury for finding our work of relevance, and I'm really honored to receive this prize. I also thank Professor Sur for introducing our topic really well. When reflecting on this prize, I'm extremely indebted to all the outstanding members of our research group, past and present, for their hard work, dedication, creativity, and persistence that has enabled us to be where we are today. I stand here on behalf of all of them to celebrate this award. I also thank all the wonderful collaborators with whom I've had the privilege of working with since starting my independent career, since our research falls at the interface of biology and chemistry. And I'm really happy that quite a few of them are here today. Thank you all for coming. On a personal front, I am blessed with a wonderful family and a terrific group of friends, quite a few of whom are here today. A couple of special mentions. Firstly, my parents who are here today. Since childhood, they have nurtured my curiosity. They have instilled in me the value of education and a life of continued learning. Secondly, my independent career would surely not be possible without the support of my wife, Neeraja, who is also here today. I'm in awe of her kindness, the professional sacrifices that she has made, and most importantly, her tolerance of my many shortcomings. Lastly, I would not be here without wonderful teachers and mentors that I've been fortunate to have in my life, especially my graduate advisor, Professor Frank Rochelle, and my postdoc advisor, Ben Cravat. Both Frank and Ben have taught me how to be a researcher. They've taught me how to choose meaningful problems, how to develop strategies to tackle them head-on rather than shy away from them, how to communicate findings with clarity, and most importantly, how to be kind and generous to others. Thank you very much again to the Infosys Science Foundation and the jury for selecting us for the award.
Thank you, Dr. Kamath, and congratulations. And thank you, Dr. Sur, for that very concise biology class, which was better than what I got from ChatGPT, definitely. And, my takeaway at the end of it is what my wife always tells me. Listen to your body, it's smarter than you. Next up is mathematics, a discipline where the truth plays odd pranks. Our laureate in this category this year is a professor at the Indian Statistical Institute in Kolkata. She's one of the youngest and one of the few women to receive the prestigious Shanti Swarup Bhatnagar Prize in Mathematics. Her work has resolved a very long-standing conundrum in mathematics. I will certainly not be able to describe the abstract complexity of her work, and so to tell us about it, I'm very happy to introduce to you the jury chair for mathematics, Professor Chandrasekhar Khare. Professor Khare is from the University of California in Los Angeles. He's a number theorist, and his work with the Jean-Pierre Wittenberger proved Serre's celebrated modularity conjecture. He has received a number of honors and awards in recognition of his work, including the Fermat Prize in 2007, the Cole Prize in 2011, and the Infosys Prize in 2010. Professor Khare was elected as a Fellow of the Royal Society. Please welcome him here to present the Infosys Prize in Mathematics. Professor Khare.
So the Infosys Prize 2024 in Mathematical Sciences is awarded to Neena Gupta. She is a professor at the Indian Statistical Institute of Kolkata. She has been awarded for her work on the Zariski cancellation problem, a fundamental problem in algebraic geometry, first posed in 1949 by Oskar Zariski, one of the founders of the modern version of the subject. In 2014, she proved the striking result that Asanuma's three-dimensional affine variety yields a negative answer to Zariski's original cancellation problem in positive characteristic. So the jury consisted of LNNO from Berlin, Meena Mahajan from Chennai, Siddharth Mishra from Zurich, and Deependra Prasad from IIT Bombay. So let me try to unpack the citation a little. Dr. Neena Gupta's work is in a subfield of pure math called affine algebraic geometry. Zariski's problem, or conjecture, revolves around the cancellation property for polynomials, essentially asking whether an algebraic object that becomes the polynomial ring after adding a variable is itself such a polynomial ring in some variables. So in more geometric terms, the problem asks if two geometric objects have the same structure after adding a dimension to them, which is like considering cylinders over them, then do the objects themselves have the same structure? Dr. Gupta showed that in a certain important case, contrary to what one might expect, the answer is in the negative. Thus the innocuous-looking move of adding a dimension can destroy information. Now, I would like to make some more general philosophical remarks about the nature of Dr. Gupta's work and the fact that it settled a conjecture in the negative by means of constructing what is called a counterexample. So the field of algebraic geometry in which Dr. Gupta works goes back to the work of the French mathematician and philosopher René Descartes in the 17th century. One of his very important contributions was to introduce coordinates in geometry, thus bridging the worlds of geometry and algebra. So bridges which you build between different concepts in mathematics are very valuable, like, for example, this very elegant bridge on the card I've been given. So Descartes built a very elegant bridge between algebra and geometry. A geometric object like a curve in space after Descartes could be expressed as the locus of solutions of an equation. This wedding of the worlds of algebra and geometry was a powerful idea which transformed mathematics. Now, Descartes was not just a mere mathematician, but also a famous philosopher. One of Descartes' famous existential pronouncements is, cogito ergo sum. I think, therefore I exist. In fact, the full quote is dubito ergo cogito ergo sum, which is of course Latin to me, and in translation reads, I doubt, therefore I think, and therefore I am. Descartes' quote is related to an important aspect of mathematics that figures in Dr. Gupta's work, namely the role of doubt and the questioning spirit in mathematics. Mathematics, broadly speaking, consists of conjectures and theorems. What are these? A theorem is like a statement of fact. The Pythagoras theorem, which states a relation between side lengths of a right-angled triangle, is an example. In mathematics, the statement of a theorem has to be followed by a proof. To quote a theorem is almost like casting a spell. The tremendous effort and ingenuity expended in proving a theorem is compacted into its great power that can be activated by simply quoting it. A conjecture, on the other hand, is like an unfulfilled fantasy in the world of mathematics. The best conjectures are more than just guesses, often having passed multiple plausibility tests. A conjecture reflects the sunny yet cautious optimism of the mathematicians who propose it, and finding the proof for one is no easy venture. Perhaps that is why a conjecture becoming a theorem is like a dream come true or a fantasy coming true. Dr. Gupta, on the other hand, had the gumption to look critically at the Zariski problem or conjecture and disprove it in the special case of positive characteristic. Mathematics progresses on the strength of new ideas and accommodates both the optimism of work that proves a conjecture and the constructive skepticism which may result in the disproof of a conjecture, and which then leads to nuance in one's expectation of what is true. So thus, Dr. Gupta's work can be summarized along the lines of Descartes' famous pronouncement, I doubt, therefore I think, therefore I am, as Dr. Gupta doubted the truth of Zariski's conjecture. She thought deeply about it with great intensity and ingenuity, ultimately disproving it. Dr. Gupta's audacious doubting of the Zariski cancellation problem has led her to many honors and prizes, including now the Infosys Prize for 2024. She's a role model for women who want to pursue the beautiful, but yet highly gender imbalanced subject of mathematics that is full of conjectures, waiting to be proven, or indeed, like in Dr. Gupta's case, disproven. She has done all her work in India and is a role model for mathematicians in India. Congratulations, Dr. Gupta.
Thank you, Professor Khare. And here is Professor Neena Gupta talking about her fascination with solving puzzles.
Whenever there are tricky problems or puzzles, I love to solve it. That is what motivated me to do mathematics and to later take up affine algebraic geometry. There are several interesting problems which keeps me occupied all my day. It was during my PhD days when Professor Asanuma was visiting ISI, I came across his paper where I found a three-dimensional ring which could be a counterexample to the Zariski cancellation problem. I told him that we can do this. He was very concerned and in kind words he said, it's very difficult and you should not waste time on this. The next year I was able to solve it. The cancellation problem is actually true for dimensions less than equal to 2. And my result shows that in positive characteristic, cancellation in higher dimension does not hold. You should take up mathematics if you love it, if you are passionate about it, if you enjoy solving problems. Research is a 24/7 job. You cannot separate a researcher from their own self.
Professor Gupta is not able to join us in person this evening as she was selected to deliver the very prestigious Emmy Noether Lecture at the 2025 Joint Mathematics Meetings in Seattle this week of the American Mathematical Society. But we are very pleased to welcome on stage her husband, Vishal Saraogi, and her daughter, Manya, to accept the prize on her behalf. So may I request them to come on the stage, please, and may I request Mr. K. Dinesh, the anchor trustee for this category, to join Professor Kare for the presentation. And may I request Professor Peter Sarnak to present the Infosys Prize in Mathematics to Professor Neena Gupta. Thank you, Mr. Dinesh. Thank you, Professor Kare. Thank you, Vishal and Manya. Proud of your mother, Manya? Well, Professor Neena Gupta pre-recorded this acceptance speech for us. Can we play her video, please?
I thank the Infosys Science Foundation, the honorable jury members, for considering my work worthy of this prestigious international prize. I regret not being present here physically because of the 2025 Emmy Noida lecture to be delivered at the joint mathematical meeting organized by the American Mathematical Society and the Association for Women in Mathematics. It is really unfortunate that I will miss the opportunity of interacting with Professor Peter Sarnak. I remember talking with him during his visit in TIFR. At this moment, I should thank all my supporting pillars. I have been guided and taught by many people. I cannot forget my teachers from school and colleges who have always been kind and encouraging to me. I am very, very thankful to all my teachers of ISI Kolkata who have been always encouraging and kind to me, who introduced me to this world of mathematics. A special thanks goes to Professor S.M. Bhatwadekar, my grand supervisor, who taught me various techniques which have been very useful in my subsequent research. I am also thankful to the TIFR authorities who have helped facilitate my visit to TIFR so that I could interact with Professor Bhatwadekar, Professor Gurjar, Ravi Rao, and many other people. I also thank Professor Asanuma, Professor Onoda, and Professor Kuroda for visiting ISI regularly. I also thank my collaborators. I thank my family, my parents, my brothers, my spouse, and my in-laws for all having faith in me. Finally, I would like to thank my supervisor, Professor Amartya Kumar Datta, for introducing me to this world of commutative algebra and affine algebraic geometry.
Our congratulations to Professor Gupta and her family. As they say, the study of mathematics begins in minuteness, but ends in magnificence. Well, the MIT physicist Seth Lloyd said, "Nothing in life is certain except death, taxes, and the second law of thermodynamics." This year's winner in the physical sciences category is out to disprove that, well, at least the thermodynamics part. She's an associate professor of physics at Stanford University with a PhD from Princeton. And to announce the prize, it is my pleasure to introduce the jury chair, Professor Srinivas Kulkarni. George Ellery Hale, Professor of Astronomy and Planetary Science at Caltech, and the former director of the Caltech Optical Observatories. His primary interests are the study of cosmic explosions, neutron stars, and developing new methodologies for astronomical research. His notable awards include the Alan T. Waterman Prize, the Helen B. Warner Award of the American Astronomical Society, and the Jansky Prize of Associated Universities, Inc. In 2024, Professor Kulkarni was awarded the very prestigious Shaw Prize in Astronomy for his groundbreaking discoveries about millisecond pulsars, gamma-ray bursts, supernovae, and other variable or transient astronomical objects. He's won the Dan David Prize for his contribution to the emerging field of time-domain astronomy. He's a fellow of several learned societies. Ladies and gentlemen, I give you Professor Srinivas Kulkarni.
The Infosys Prize in Physical Sciences for year 2024 is awarded to Professor Vedika Kemani. The citation reads, for her wide-ranging and groundbreaking contributions to theoretical and experimental non-equilibrium quantum matter, most notably the discovery of time crystals. The panel consists of Professor Shankar at Yale, Spencer Wadia here, right here at ICTS, Professor Yamuna Krishnan at Chicago, and Professor Yu at Scripps. The scope of physical sciences is quite large. It's physics, it's astronomy, chemistry, geology, and even paleontology. The United Nations has declared this year, 2025, as the International Year of Quantum Science and Technology. So let me give you a little bit background of quantum mechanics. In 1905, Einstein showed that light is quantized. In fact, his Nobel Prize was not for the theory of special relativity or general relativity. It is actually for showing that light, which acts like waves, which we see in rainbows and in diffraction gratings, but acts as a particle, which has been subsequently named as a photon. A few years later, Niels Bohr made a conjecture that the angular momentum of electrons in going around a nucleus is quantized. So now you can see that's a particle now, it's not a photon. And he was able to beautifully explain the discrete features of the hydrogen atom. So this is what's called as the old quantum mechanics. It had elements of classical physics with some sort of assumptions. But the year 2025 was very, very special. Within a 12-month period, there were 3 amazing papers. De Broglie made a very bold conjecture that material particles, just like photons, can also be viewed as waves, or just like photons used to be viewed as waves. Separately, Heisenberg published his seminal paper on what's called matrix mechanics, and Erwin Schrödinger established that Erwin Schrödinger developed wave mechanics for particles. So at this point, everything is waves. And that may be very difficult for you to accept, but that is the actual reality. These papers firmly establish that the underlying basis of reality lies in probability wave functions with some fundamental quantities taking on discrete values. So at the very microscopic level, it's not a continuum, it's not continuous. Thanks to quantum mechanics, which has been very difficult to understand even 100 years later, I can tell you, though I'm not a practitioner of that, I'm a user of quantum mechanics, it's always topsy-turvy. But thanks to this amazing development, we now have lasers, semiconductors, amongst many, many other technologies and inventions all of you use routinely. The same quantum mechanics also explains how stars shine and die. The quantum revolution, even though it's 100 years old, is nowhere close to being completed or even maturing fully. We still lack a quantum description of gravitational forces, and we are very much in the wilderness in our understanding of dark matter and dark energy. But now let's get on to, so these topics are, a big area of investigations amongst theoretical physicists, but a whole new dimension has come about in the last decade or so, and that's to do with the ability to manipulate atoms one by one. You can pick tweezers and arrange them in whatever way you want. And this, so you can call it as a many-body, quantum many-body systems. And one of the big applications is quantum computing. Okay. So the focus of a number of other physicists is to study the quantum mechanics of many particles. The study of many particles with interactions is also known as condensed matter. That usually means the quantum mechanics of solids and liquids. And has been a very traditional area of quantum mechanics. This big field provides the foundation of the semiconductor industry, for instance. Much of the matter around us is close to ground state, which is sort of energy, the system being in the lowest state. So condensed matter naturally has focused on things around the ground state. So, perturbations, it's above the ground state, how does it relax and so on. So that has focused on disequilibrium of such, let's call it as ordinary matter. However, the same technology that's now going into quantum computing, the ability to arrange your own artificial systems, these experiment methods allow new types of many particle systems that can be constructed that are very far away from the ground state and would not otherwise naturally exist. And all sorts of new things come about from these sorts of matter. And that's, in fact, the major focus area of Professor Khemani. Professor Khemani has made extensive contribution to the broad area of such non-equilibrium many-body systems. With Emanuel Bloch's experimental group, she established the existence of the pre-thermalization phase, which precedes actual thermalization. She has investigated fundamental theoretical issues such as thermalization and the hydrodynamic, which is a fluid mechanics description of the quantum many-body systems. She and her collaborators show how to unify traditional hydrodynamics and a recently elegant explanation of how a closed quantum system manages to dissipate. Another landmark contribution of Khemani is the discovery of a new mechanism for ergodicity breaking, now called Hilbert space fragmentation. The panel noted that starting from her days as a graduate student in Princeton, Professor Khemani stood out for her exceptional ability to collaborate with senior colleagues on equal terms to explore, synthesize, and inform. I'll now focus on one topic, because a lot of that stuff you may not be able to fully understand. Okay, so for that we'll need a little demonstration. So let's talk of time crystals. Ordinary crystals, which all of you admire, is very regular. The atoms are spaced very regularly, unlike gas, okay, which is very homogeneous, okay? And this crystal structure stays forever, in principle. There are many reasons to think space and time are in some sense not very different. I mean, that was in fact a major aspect of special relativity. So in 2012, a very famous physicist, Frank Wilczek, wondered whether you can have time crystals. That is, if you can have a periodic structure in space, can I have a periodic structure in time? Sounds reasonable, except there's this thing called the second law of thermodynamics, which treats time and space differently. So one idea is, can I make a pendulum swing forever? That would be, a pendulum is periodic in time, and can I have it go on forever? So we'll do that. So you can say, here's my pendulum, so it'll swing back and forth, okay? Now you'll say, oh, well, it'll slow down because the bob there is rubbing against the air, and therefore you'll start losing energy. Well, then you can put this whole thing in a vacuum, and it'll slow down much slower, yeah, because there's no air, the air friction goes away. However, this has many atoms in it, and a small perturbation is enough that you'll have dissipation within the wire. So you choose different materials, but we know from that this will eventually slow down. So this is a bit of a puzzle. Can you have a time crystal? So an ideal time crystal is something that will oscillate forever. Working with Google quantum computers and engineers, Dr. Khemani demonstrated a system of spins flipping back and forth between two many-body localized states without energy dissipation. That is a true time crystal. You might think that Dr. Khemani, is one of these, thinks a lot, like mathematicians lost in their clouds and so on, but actually I found that she's very practical too. When I was talking to her after her lecture yesterday, she said the technical name for this system, which goes between two states both of which are frozen like glass without losing energy. It is really pi glass, but they decided that time crystal is a bit more memorable, and that's what goes in their title of their Nature papers. So you can see she has made a lot of good street smarts. This weekend, many physicists from India and abroad are arriving here to Bangalore to attend a week-long celebration of the first century of quantum mechanics. The workshop is being hosted by our own ICTS, not far from here. Dr. Khemani is one of the participants. Even in this very distinguished group that will be assembled at ICTS next week, Professor Khemani stands out for her rare mastery of theory and experiment and ability to engage both groups in pursuit of new phenomena and a deeper understanding of known ones. Congratulations, Dr. Khemani.
Thank you, Professor Kulkarni. And here is Professor Khemani talking about the interesting space-time geometries that she is exploring. Can we have the video, please?
The type of physics I do is to ask, what are new types of emergent phenomena that can exist in systems of many strongly interacting quantum particles? With new quantum experiments, we now have access to quantum matter in a regime that we simply did not have before. For instance, strongly out of equilibrium, are interacting via interesting space-time geometries that we can control, but which simply do not exist out in the wild. We ask, what are new types of phases of matter that can exist in these exciting new settings? One striking example of such a phase is a time crystal, which is fundamentally disallowed by the laws of equilibrium thermodynamics, but which has found a new life in these settings that quantum experiments have opened up for us. We are now experiencing a full circle moment where breakthrough advances in quantum engineering are motivating fundamental new theoretical questions. And in turn, theoretical advances are pushing the frontier of experimental developments. It is an exceptionally interesting time, and we're just scratching the surface of discovering what is possible in this exciting new era of quantum science.
Please join me in welcoming on stage Professor Vedika Khemani. May I request Mr. Nandan Nilekani and Professor Kulkarni to join the presentation. And may I request Professor Peter Sarnak to present the Infosys Prize in Physical Sciences 2024 to Professor Vedika Khemani. Thank you, Professor Kulkarni. Thank you, Mr. Nilekani. Thank you, Professor Sarnak. Professor Khemani, a few words from you, please.
Thank you. Thank you to the Infosys Science Foundation, to the jury, and to my nominators. I'm so deeply honored to receive the Infosys Prize in the Physical Sciences. It is wonderful to be part of this celebration of scholarship and curiosity-driven research, which drives us each day towards an unimaginably exciting future. The values embodied by Mrs. Sudha Murthy and Mr. Narayan Murthy of simplicity, hard work, and an unapologetic pursuit of excellence are an inspiration for all Indians, and I'm particularly glad to now be connected to the Infosys family in a small way. We're living in such a golden age. There's so much inspiring science happening today that it feels both humbling and honestly a little bit unsettling for my work to be selected among so many other remarkable contributions. But this award is by no means mine alone. It represents the effort of brilliant collaborators, students, and fellows, and I'm immensely grateful to them. It's an extraordinary privilege to be able to spend my days doing science,
to live in the world of ideas, and to learn every day from brilliant minds across the world. That in itself is a bigger reward than anything I could have imagined for myself. And I was only able to access this wonderful life because of the guidance and encouragement of my many mentors, from the teachers who encouraged my budding interests in my early days, to the steadfast and patient guidance of my PhD advisor, to the support of my senior colleagues and collaborators at Princeton, Stanford, and elsewhere, even today. Thank you to each of you. Finally, this recognition is particularly meaningful because I get to celebrate it here in India with my family, my grandmother, who's in the audience, my parents, my husband, my aunts and uncles and siblings. Their belief in me and the support and love and encouragement from each of them gives me the courage to dream without any bounds. Thank you again.
Thank you and congratulations, Professor, for being like the time crystals you're investigating, going on indefinitely without losing any energy. Well, those were our 6 Infosys Prize laureates for this evening. Let's give them a big round of applause. And may I request Mr. Gopal to accompany our chief guest to the first row of seats. Music is a universal means of celebration, and I invite you now to sit back and enjoy the specially curated performance by the Gooseberry Ensemble, the trio consisting of Sayan Sinha on violin, Arina Sharma on cello, and Abhishek Gonya on keyboard. Ladies and gentlemen, the Gooseberry Ensemble. The Gooseberry Ensemble and the magic of the strings for those moods of reflection and celebration. Thank you, Sayan, thank you, Arina, and thank you, Abhishek. And now, to formally introduce our chief guest of this evening, I invite Mr. Narayana Murthy, the founder of Infosys and trustee of the Infosys Science Foundation, to the podium.
It is indeed a great pleasure and a privilege to introduce Professor Peter Sarnak, our chief guest. I was privileged to have been a trustee of the Institute for Advanced Study at Princeton for 8 years, from 2016 to 2014. I have had the pleasure and the privilege of sitting through a few of Peter Sarnak's presentations. When he spoke, every trustee, irrespective of what background he or she came from, listened to him with attention, because he has that ability to communicate complex ideas in a very simple way. Professor Peter Sarnak was born in 1953 in Johannesburg, South Africa, and he is currently Gopal Prasad Professor of Mathematics at the Institute for Advanced Study at Princeton, and Eugene Higgins Professor of Mathematics at Princeton University, United States. He received his bachelor's degree in mathematics from the University of Witwatersrand, South Africa in 1975, and his PhD in mathematics from Stanford University, US, in 1980. He has served as a professor at New York University, at Stanford University, and at Princeton University. He was a member of the Institute for Advanced Study at Princeton between 1999 and 2002, and between 2005 and 2007. He has been at IAS as a professor since 2007. He is a member of the US National Academy of Sciences and a fellow of the Royal Society of London. Professor Sarnak is the recipient of several awards, including most recently the Shaw Prize in Hong Kong in 2024, the Sylvester Medal from the Royal Society in 2021, and the Wolf Prize in 2014. Ladies and gentlemen, it gives me great pleasure to present Professor Peter Sarnak to you.
Okay, thank you. Thank you, Mr. Murthy, for your very kind introduction. It is a great honor for me to be part of the Infosys 2024 Prize ceremony, recognizing the achievements of these young scholars whose brilliant research has advanced and helped shape their fields from mathematics, physics, and computer science to life sciences, social sciences, and humanities. Over the years, I've witnessed firsthand the immense talent and impact of Indian mathematicians, physicists, and computer scientists, and as is clear from the description of this year's winners and what we've seen over the last 2 days, this tradition extends across all the disciplines and to all the 2024 prize winners. The annual recognition of such world-leading scholars by the Infosys Science Foundation is an inspiration to students both in India and globally. Speaking at such a celebration of scientific advances, many of which involve mathematics, is an opportunity for me to reflect on my field, number theory, and its evolution in becoming applied and to speculate going forward. So my small speech will be divided into 3 parts. And I'll start with the first part, which is some classical number theory, which you see here. So you might ask, what is number theory? The great 20th century visionary André Weil, who, by the way, was shaped mathematically and otherwise through his visits to India, punts that he puts aside the answer when trying to give a definition in one of his books by quoting the poet Housman. If you ask a fox to define a rat, he may not be able to do it, but when he smells one, he knows it. Well, when Weil, that is, smell number theory, I think I know it. And then he carries on to describe what he thinks is and is not number theory. Anyway, for us, lower, not André Weil, God gave us those numbers. We'll be sort of quoting that. They have a concrete beauty that suggests truths which are easy to state and often very difficult to prove, and it's what attracts many of us number theorists to the field. So I want to give you three classical examples, and I'm going to give applications, so these will feature in them. So prime numbers, these are whole numbers which are divisible only by themselves and by 1. And it's one of the very earliest theorems, proved by contradiction usually, that there are infinitely many primes. Not completely obvious fact, proved by Euclid. We'll be using the infinitely many. The great mathematician Gauss, also a great number theorist, in 1796 proved the following, which is his Eureka theorem. He was about 19 when he proved this, and he had been trying to do this, and when he did, he was very excited, and he writes it as num equals delta plus delta plus delta. Every positive number can be written as at most 3 triangular numbers. So that's a highly non-trivial statement, because you take a very large number. I'm going to tell you what a triangular number is in a second. Triangular number is a number that you can form by taking 1, that'll be the smallest triangular number, and then you take 1, the top of the triangle, and take 2 below it, that will give you 3, and then if you continue, you'll get 6, and so on. If you go up to level t, you'll get t times t plus 1 over 2. So delta t is the number of vertices in a triangle like that, and he and others were trying to understand this Diophantine equation, that every number can be written as a sum of at most 3 triangular numbers. By the way, the number delta 100 is 50-50, and there's I don't know if it's a true story, but when Gauss was probably a toddler, his teacher was always, caregiver was trying to keep him quiet, so she said to him, why don't you add the numbers 1 to 100? And he said, oh, it's 50-50. And what? She said, well, you take 1 plus 100 is 101, 2 plus 99 is 101, 3 plus 98 is 101, so it's 101 times 50, which is 50-50. So he liked these numbers, and he showed talent early on. Anyway, that's it's a remarkable theorem, proved when he was 19, and he wrote a whole book, which is for many of us, the beginnings of modern number theory, called Disquestione Arithmeticae, which developed the theory of such equations, Diophantine equations. Gauss was, of course, one of the great mathematicians. Everybody knows Gaussian fields, Gaussian laws, statistics. He did astronomy. But he thought of number theory as very beautiful, but not very useful. And he called it the queen of mathematics. As earlier, some people call mathematics the queen of science. Number theory is the queen of mathematics. Probably indicates that he doesn't think it's very useful. All right, let me give you the next example. Fellow who came a little after Gauss, Jacobi. He introduced something called modular forms, which are the remarkable tools of modern number theory, allow you to do things that no other method allows you to do. Somebody should write, maybe Carre should write the paper, The Unreasonable Effectiveness of Modular Forms in Number Theory. Anyway, they were introduced to number theory by Jacobi, who was looking at a problem very similar to Gauss. In fact, Gauss, I'm sure, thought about this, is how many ways can you write a number as a sum of 4 squares? So that's an equation in whole numbers. So n is an integer, and you want to write it as x1 squared plus x2 squared plus x3 squared plus x4 squared, and you want to count the number. It was known by Lagrange that every positive number is a sum of 4 squares. And Jacobi gave this amazing formula. Now, that formula looks a little complicated maybe to the non-mathematician. So there's a sum, a fancy sum sign, d divides n of d times 8. So if n is prime, there's only 2 divisors. It would mean every prime number, odd prime number, can be written as a sum of 4 squares in 8 times p plus 1 ways. That's just incredible that mankind can prove it. That you can observe it numerically is probably not surprising, certainly the kind of thing that a machine could do. The Indian math legend S. Ramanujan put forth a far-reaching conjecture related to such Diophantine problems, known today as the Ramanujan conjectures, whose solution in 1973 is one of the highlights of 20th century mathematics, relying on algebraic geometry methods of Alexander Grothendieck and the final proof was delivered by my colleague at the Institute for Advanced Studies, Pierre Deline. Its flavor with arithmetic geometry at its core is what Weil says he recognizes as pure number theory. When he was saying, I smell it when I see it. This was to the epitome of number theory. All right, that is the Ramanujan conjecture. I'll return to it later. It's a very specific series, and only Ramanujan could make the conjecture that tau of p is less than or equal to 2p to the 11 over 2 for every prime p. An extremely deep conjecture that, as I say, takes the highlights of 20th century mathematics to prove it. All right, with those gems from the past, let me turn to part 2 of this talk, which is some applied number theory. So with the arrival of the digital age, it is natural that discrete mathematics has joined traditional calculus, partial differential equations, and have been for centuries in describing physical phenomena as the language of applied math. So remember, Gauss was saying it's the queen. I can give you many other quotes of number theory never to be useful by a great number theorist. But many of the questions in discrete math come from, in modern times, and especially ones also coming from quantum mechanics and quantization rules and discretization of spectra that lie below the surface are of a number theoretic flavor. So there's probably no more impactful question that I've already mentioned in number theory than that of the impact on cryptography. So public crypto systems in particular. Their security is based, so public security systems, Diffie and Hellman, is based on the existence of a one-way function, a function that you can compute quickly one way, but not in the inverse you can't compute quickly. And this gives you the advantage, and it's about how fast you can compute. And the standard RSA scheme for public key cryptography is based on there being a one-way function, and the one that was proposed and is probably still used is RSA, which is based on the fact that if you take two large prime numbers, and you can test whether a large number is prime. In fact, the very first Infosys Prize was given to Agrawal. I happen to be on the committee. Was given to Agrawal for proving with these two undergraduate students, Kayal and Saxena, proving that you can test very quickly whether a number is prime, a very large number. Now take two very large numbers which are prime, multiply them together, you get a much bigger number, and if you know the factors, one of the factors, you can get the other factor. But suppose I give you the product, can I find the factors quickly? All of classical crypto system is based on the fact that you can't. I personally believe you can, but I haven't produced a way to factor, so you can ignore me. Modern crypto system is based on that, and a dramatic event happened connected with this new quantum world that this year is seeing 100 years of quantum mechanics. Peter Shor showed that if you could build a quantum computer, then it could factor quickly and break all systems that are based on factoring. So you'd have to find some other way to secure your crypto systems. And if there's an impact on factoring, this is it. We all know how much money has been put in by companies and governments to build a quantum computer. In fact, let me say a word now about a quantum computer and Ramanujan. This is not so well known. If you buy an IBM quantum computer, I don't know what it does actually, but you'll own the first quantum computer that exists for $130,000 or something. I'm making this a little up. It's what it was some time ago. You have to write a code, and to write a quantum code, you actually have to have gates, and quantum gates consist of 1-bit qubit gates, and you'll have to use these gates which they offer you to use. And these gates it's interesting that these are just 2x2 matrices over there, as you can see, and you've got famous physicists named after the 2x2, these 2x Pauli X, Pauli Y, Pauli Z, a famous mathematician, Adamard matrix. Those matrices generate a finite group of rotations, and you need a universal gate set if your computer is going to actually be better than a classical computer. So they add this pi over 8 gate called the T gate, and you have to use it. Now, the incredible thing is this was added by IBM. I'm not sure exactly how they chose it, but if you look at those gates, they work extremely well. And in fact, the reason they work so well, and there's a proof of this, is based on the Ramanujan conjecture. It's what assures you that those gates are very efficient in terms of exploring 1-qubit gates. So Ramanujan's conjecture has profound implications in the architecture, at least IBM's gate set. All right, I will give you one more example, and then I will talk about some speculation about the future and computation. So fullerenes, these are carbon molecules, carbon clusters, which have been produced in nature. C60, the buckyball, is an example. It was the first significant one found, and in fact won these 3 fellows a Nobel Prize. Mathematically, what they are, these carbon clusters, are cages on the sphere so it's some arrangement on the sphere. I'll give you a picture in a second, where all the faces are either hexagons or pentagons, and nothing else. There's a lot of mathematicians and physicists, chemists who were involved in this. This is what they look like. So the football is an example of such a thing. It's everyone's favorite. There's one there on the left there which has just got pentagons. The football's got, every one of them's got 12 blue guys, which are pentagons, and otherwise, when they get big, they're always exactly 12. That's a little piece of mathematics. Topology, as it's called, and then the rest are all hexagons. And the question is, if I have n atoms, how many carbon clusters can I make? So how many of these are there with n sites? How many fullerenes there are? And this was not unsolved till this year. In a remarkable recent paper last year, now it's 2 years ago, I apologize, using some very ingenious ideas of Thurston, a great geometer from the last century, work from the last century, and an advanced number theory of the type which comes from modular forms on unitary groups, and a formula which is exactly like the formula that I showed you of Jacobi, gives an exact formula. And remember, Jacobi's formula was the sum d divides n of some simple expression. Okay, in this world, this is simple. That's just some polynomial of degree 9. And it's a sum d divides n of that is the exact count. It's remarkable. Number theories produce the exact count. I don't know that that's so useful to chemists anymore, but it is beautiful, and it's a beautiful application of number theory that one can answer such a question. All right, I would be surprised if any chat GPT could come up with this. It will, because this is now on the archive, but without that. And in fact, that brings me to the final part of my talk, which is part 3, where I'm going to speculate about something I shouldn't be speculating about, but I thought this is a good occasion to speculate about it. To be honest with you, I'm one of these older mathematicians who's saying, well, all this AI is not going to go anywhere in terms of doing something for us. But my younger colleagues who are who I've gave great appreciation of, are putting pressure on me and saying, well, what would it take for you to admit that this thing is doing something really interesting and that this is going to be the future of mathematics, or mathematics may look very different in 50 years? And they're right, so I gave it some thought, and this is going to be my speculation, and I'm actually thinking about it much more seriously, but let me introduce it here. So speculations about theorem proving. So calculations and computations have always been central to the development of number theory. The question of whether and how the recent explosion of statistical machine learning will impact number theory, or more generally, pure mathematics, in, say, the next 50 years, is one that working mathematicians are beginning to and should be addressing. My brief take on this below is that of a mathematician / former chess player who is watching from the sidelines. So this, coupled with speculations about technology, may well prove to be very misguided. In any event, the story about chess-playing machines has gone through some very key stages. While chess is finite and has artificial rules, it is too large to be analyzed by brute force, and it comes with an elaborate man-made theory. It may offer some insights as to how the tale of machines doing mathematics will evolve. The strongest chess programs are Stockfish and AlphaZero and their derivatives. AlphaZero is stronger than Stockfish, and both beat humans handily. Stockfish is programmed according to chess theory, and it is an extension of chess master play. It calculates faster and deeper, never makes shallow tactical mistakes, and it makes use of large databases of recorded games. Its play is explained by chess theory and can be understood by strong players. AlphaZero, on the other hand, makes no use of chess theory or any databases. Instead, it generates the latter, playing itself many times, and uses statistical machine learning to improve its guess for the next best move in any position. It is better at doing so than any human or any other machine. And as such, it has passed a statistical complexity threshold special to the game of chess and its size. AlphaZero offers no understandable to human explanation for its guess. This appears to be a disaster for chess theory, but I would argue the opposite. AlphaZero plays the game much the way, and occasionally with some flair, that the best players have been doing so for the last 100 years. This gives an external confirmation that the heuristics provided by chess theory are remarkably effective in approximating the best move in most situations, or at least AlphaZero's best guess for that move. AlphaZero and its derivatives have been around for 7 years, and as far as I can tell, its impact on competitive chess is quite small. For preparation, it seems that most experts use Stockfish and its derivatives to analyze innovations and variations. Some masters say they get some understanding and inspiration from AlphaZero and its descendants. It would be very interesting to know if and how the newly crowned world champion Gukesh, congratulations, if he uses AlphaZero. So I want this slide to be here for what I'm about to say. That should be up there. Okay, so that's the story with chess, and AlphaZero is a major thing. The idea of theorem-proving machines presents itself as soon as one formalizes mathematics with axioms and rules of deduction. The theorems being statements that can be derived in with a finite number of deductions. There are fundamental differences to chess, of course. Firstly, the universe of mathematics is infinite. Second, the rules are God-given, at least if one starts with whole numbers, number theory, and their arithmetic. Thirdly, the theory is undecidable. That's a theorem of Gödel. That is, there are statements that, and even interesting ones, proved by my PhD advisor, Paul Cohen, whose truth or falsity cannot be decided within the formal framework. By a theorem-proving machine, I mean a device which has the axioms built into it. It knows the axioms and the rules of deduction, and it accepts as an input a statement that it's supposed to prove or disprove. We give it some time to think, after which it either comes back with a formally correct answer, or it says that it does not know. So where do we stand today with theorem-proving machines? Perhaps at the stage that chess was in the 1950s with the arrival of the modern computer. There are effective formal programs that can check correctness of proofs and do so interactively. There's a laborious global effort by mathematicians to formally check and record advanced mathematical theories into these systems. These projects should be complete and running efficiently long before our 50-year timeline, and they will be available to our theorem prover to use. At the center of my speculation is the following. I'll call it the AlphaZero test. The theorem prover has no access, this machine in 50 years, has no access to any outside data, just like AlphaZero, or any theory. And we input the statement of the Ramanujan conjecture. And in its form that he formulated, which is elementary, it will be able to intake very easily, and which is explicit. And we ask it to decide, is it true or false? I postulate that it will fail this test, and that it will fail similarly
on most of our theorems whose present-day proofs make use of abstraction, conceptualization, and the development of a body of theorems which we call mathematical theories. These theories are what allow mathematicians to understand and communicate ideas and proofs, and also to internalize why various statements are true. The proofs, if written out from scratch, would be quite long. So I'm postulating that the threshold which was passed by AlphaZero for chess will fail here. That its process of generating proofs towards a goal via self-correcting guesses using statistical machine learning. Of course, in 50 years, there'll be other kind of AI, which I can't say anything about. But anyway, those devices, I'm postulating, will recover few of the theorems of our theory. If this postulate is wrong, the impact on mathematics will be dramatic, and we will be in a position of knowing statements of great interest to us are true and even proven, but not being able to understand why they are true. Since understanding is such an integral part of doing mathematics, we'll have to rethink what mathematics is. So to continue this, I'll assume that this postulate is correct, and I'll call the theorems that our prover can prove elementary statistical. The point, I'm nearly done, the point of our discussion is to allow our proving device to access any information that might be useful for its learning and correction. If we were to input the statement of the Ramanujan conjecture, it will instantly answer yes and refer to the database of mathematics, whereby then this has been formally checked and recorded. In this way, at any point in time, we have a body of mathematical theorems and theories, and the question is, what further statements can our statistical theorem prover deduce? Again, I postulate, and here I know many mathematicians disagree with me, especially younger ones, that this class will be limited. I'm saying it will be limited. In the ordinary mathematical terminology, for which it will have successes, are the problems for which are already on the ballpark and our current theories can more or less handle, and I'll call them elementary statistical derivatives of our theories. Indeed, these are the problems that most of us try to solve most of the time. The proving device will expedite the determination and understanding of what these are and serve as an assistant to resolving them. As such, these theorem provers will be important, very important tools for mathematicians. I imagine it being something like Stockfish is for competitive chess players. In any case, whether this class is limited or more expansive, mathematical theory will be at its basis. Of course, the theory and its formulation and execution will evolve naturally with these developments. And I expect that mathematicians of my generation, were we to see any of this, we would be able to recognize and smell it as mathematics. So let me end by congratulating the winners again on their fine accomplishment to date and wish them luck and success going forward. Thank you.
I'll collect that for you. Thank you, Professor Sarnak. For those lessons on number theory and breaking it down for us, and also for your thoughts on the future of mathematics in the age of AI. Thank you. Well, as we draw this evening's program to a close, may I now request Mr. Salil Parekh, the CEO of Infosys and trustee of the Infosys Science Foundation, to deliver the closing remarks.
Oh, that was just incredible. So thank you, Professor Peter Sarnak. It's just unbelievable the way you were able to share with us what the journey was and also the speculation. Of course, your views on artificial intelligence put a different spin to Infosys in the future. So it's been an incredibly inspiring evening, a real absolute pleasure to be with all of you. Thank you for being here for this 16th year of the Infosys Prize. It's really a special honor to celebrate the achievements of all of those who've been the recipients of the Infosys Prize. The range of their work is absolutely remarkable, from time crystals to social networks to hearing and using artificial intelligence, to the oceanic routes, to lipids, and of course, to proving a conjecture in math in the negative, all of which I fully understood, so don't have any doubt about that. It was exciting to listen to the wonderful way in which the jury chairs shared what the work was, and that really made it very useful for everyone to follow and to see the depth of the work that each person had done. Once again, it was a real privilege to hear you, Professor Peter Sarnak, and just to try and digest some of the things you shared with us. A sincere thanks to all of the jury members and to the jury chairs for that sort of detailed work in going through what was a host of nominations and some really deep work that many others have done and the recipients have also done. Several of the members of the jury are here in person, so thank you for being here in addition to the jury chairs. The government of India has, in the way it's put this together, been extremely far-sighted in making this prize money for the Infosys Prize for the recipients in India. It's tax-free, and that's a huge, huge benefit to them. So a huge thanks to the government of India. And it's a big investment into the future of our country. In this 16th year, and as I've seen this over the years now, I'm even more amazed. I want to thank the trustees of the Infosys Science Foundation for their incredible vision and foresight. Sometimes you wonder, when you sort of first get a glimpse of this, what is the real application of some of these things? But when you hear this over the years, and it has a long journey yet to go, for me, it's incredible to see the vision come to light every year in this evening. Infosys, the company, of course, is really proud to be a strong supporter of the Infosys Science Foundation and to be so closely associated with it. A huge thanks to the team that supports the Infosys Science Foundation, Bhavna, Swati, Serene, and Shruti, and for everyone else at Infosys that have helped to make this evening, and actually the whole year, because there's a lot of events that are programmed by that team come together. So thanks again for everyone joining in this evening. We're looking forward to celebrating and enjoying the evening dinner and the rest of the time, interacting with all of the people who received the prize, all of the jury chairs, and Professor Peter Sarnak. So thank you all for the evening, and see you there. Thanks.
Thank you, Mr. Parekh. And now is the time for gratitude. And so may I request Mr. Narayan Murthy to join us on the stage to present a token of our appreciation to our chief guest and to the jury chairs. So may I call upon Professor Peter Sarnak first. And now the jury chairs. Professor Kaushik Basu. Professor Kaushik Basu. Professor Jayati Murthy. Professor Akhil Bilgrami. Professor Mriganka Sur. Professor Chandrasekhar Khare, and Professor Srinivas Kulkarni. And if you could have everyone together for a group photograph. Thank you, Mr. Murthy, for orchestrating that. Ladies and gentlemen, the chairs of the jury. Thank you, jury chairs. May I request Mr. Murthy, Professor Sarnak, and may I invite Mr. Gopal Krishnan onto the stage, please. And can we have all of the winners with their certificates to join us on stage for a group photograph? Thank you especially Vishal and Manya for joining us. Ladies and gentlemen, please applaud once again the laureates of the Infosys Prize 2024 for their outstanding achievements and our best wishes as they carry on their fantastic research. Smile for the photographs. And thank you. Thank you, everyone. Please take your seats. Well, with that, my thanks to everyone in the audience for sharing this special evening with us. Please use this time to switch on your mobile phone so you don't miss any calls from here. Well, dinner is served at the Prince of Wales Lawns that is adjacent to this venue. Have a very pleasant evening and see you next year. Thank you very much.